Hi class, let's just hop right into it. Here's the next hypothesis testing for when we're here. We're going to be testing or doing a hypothesis test for population mean. So you can see here's the question. I'm going to get right into it. As we talked about in the last video, we're just going to keep working through all these steps, and I'm going to kind of guide you through each of the problems and how I know what kind of problem we're dealing with. Okay, so let's read this question. The average waiting time in a local clinic is known to be 23 minutes. In an effort to reduce the wait time, a new system for processing patients is tested. The wait time of 20 patients is recorded in the new system, and the following statistics are determined. Among that group of 20 patients, X bar, the sample mean, was 19.25 minutes, and the standard deviation for any one of the patients was 1.2 minutes. Now, does that mean there's sufficient evidence to suggest that the new system has had the desired effect? Okay. Well, first of all, let's start to put together what is the desired effect. We want to reduce the wait time. So that's going to be helpful when we build our hypothesis. So we know what our null hypothesis is here, because again, that's what we're assuming the world to be prior to doing our test. Well, the average waiting time in a local clinic is known to be 23 minutes. You know, that sounds to me like that's what the world is assumed to be before there's a test. And so whenever you're doing these hypothesis testing and you get to the null hypothesis, there should always be equality there. Mu equals some value. So in this case, mu equals 23 minutes. 2, H1, this is the claim we're trying to determine if it's true or not. Well, we're asking, we want to reduce the wait time. So we need to say, well, now mu is less than 23 minutes, right? Because we need to show that we want to see if that new system, after we've tested it, has it decreased anything. Now 3, because we're trying to figure out a population mean, we know we're going to be kind of working, well, first of all, is this a one-tailed or two-tailed? Before we get into anything else. Which one? It's going to be one-tailed because again, this is less than. If this were not equal to, it would be two-tailed. But anytime that it's less than or greater than, that's always going to be your one-tailed. The next thing to look at is what is our sample size? Because that's going to decide when I find my rejection region, because that's, again, the third step, right? The first step, state the null hypothesis. Second step, state the alternative. 3, determine the rejection region. Well, what we're going to have to do is, in order to determine that rejection region, we need to know if we're dealing with a standard normal distribution or a t-distribution. Well, in this case, n equals 20. Well, this is less than 30, so it's a small sample size. So what we're going to need to do is we're going to have to work with a t-distribution. Now, in the question, just like before, we're going to make the assumption that alpha is equal to 0.05. They ask us to make that assumption. So, you know, that's 95% confidence in our procedure. So now, when you're doing this, we need to find what T alpha is in the t-distribution. And remember, when you're doing that, the way you figure that out, just like when you're doing confidence intervals, the way you figure that out is you go to that t-distribution table. Okay? And this is where remember when we were in the confidence interval video, I was talking about, well, one-tailed, two-tailed. The confidence intervals were always two-tailed. In this case, the confidence interval, it could be one-tailed or two. Well, these aren't confidence intervals, but this is why they say one-tail for when you're doing these one-tailed tests. So T alpha, we're trying to find one of these numbers, and that's going to give us our T alpha. Because this is less than, if I were to draw this out, this is going to, the T distribution is just a funky looking normal distribution. So because this is mu is less than 23, this means that our rejection region is going to live down here. Okay? If it were mu is greater than 23, it would now live up here. But it isn't, so our T alpha is going to have to be a negative number now, because remember, on a standard normal distribution, this is always a 0. This is always negative. So T alpha, we look here. We know that alpha is 0.5, so we're going to be in this column. And the degrees of freedom that we're working with here, if n is 20, df is equal to n minus 1, which is 19. So let's look on the table here. 19 and 0.5. So 19.5, 1.729 is what I get. 1.729. So this is equal to negative 1.729. All right. So from there, we know that this is equal to negative 1.729. Now in the fourth step, we want to calculate that test statistic. So we need to go to our formula sheet. That's the next part of my step. I go to my formula sheet. I find the test statistic corresponding to t. Well, where would that happen to be? Actually, it's pretty straightforward. Yes, this is z is equal to x minus mu, but t is actually exactly the same. It's not written on here, but it may as well be because it's the exact same thing. T is x minus mu over sigma. It's exactly the same procedure. So t equals x minus mu divided by sigma. And when I calculate this, just give me 1 second here. I'm just looking on my chart beside me. Oh no, sorry. Actually, I'm giving you guys the wrong information here. It's not exactly the same. Sorry about that. It's this one over here. Okay. It's this one right here. You know what? Okay, so it's this one right here. So we're going to compute this. So this is t equals x bar minus mu over s over the square root of n. So this is equal to, well, x bar that in the sample that we took was 19.25 minus mu. Mu was equal to 23 divided by, well, s is 1.2, and this is being divided by the square root of 20 because n is 20. Okay, so this, it just usually takes a couple steps to figure out. I like to figure out this bottom part first. 1.2 divided by 20 equals, so t equals on the bottom 0.2683 on the bottom, and then on the top we have 19.25 minus 23, and then divide by 0.2683. Sorry, 19.25 minus 23, so I get negative 3.75 up top. Divide that by 0.2683, and I'm going to get negative 13.98. And so negative 13.98, you can bet that's definitely in that rejection region over there. So this is negative 13.98. And so then our conclusion, 5, is that we reject the null hypothesis with a 5% chance of type 1 error. Okay. Oh, and sorry, I guess we should put the state the conclusion of our analysis is that there is sufficient evidence to suggest that the new system has had the desired effect. All right, see you in the next video.